If I persuade you to leave here paranoid, then I will have succeeded. You should all be paranoid. To begin with, I really want to thank lots of people who've handed me lots of puzzle pieces I've assembled, found a few myself, but mostly it's other people's puzzle pieces. My apologies if I've missed acknowledgments that I should have. Most of you know this stuff, but I need to remind everyone of it. TCP will, of course, fill any buffer just before the bottleneck of a path. There is a pretty much unstated design assumption that there will be timely signaling of congestion in the network by packet loss. If you don't do this, you get into a world of hurt, as you're about to see. We judge all other transport protocols by whether it's at least as good as TCP. What happens if we've violated this presumption? And a fact that seems to lots of people miss, maybe not in this audience, but in most audiences, is that a small amount of timely packet loss is actually necessary for TCP to behave correctly in a congested network. And by the way, we always are running in a congested network these days, just not where we were in the 1990s as commonly. There's also this mythology I'd like to puncture, which is the bandwidth delay product, which is indeed true for a single flow, but we don't know what the delay is, typically. We've now put all sorts of boxes in the middle of the network to minimize delay. And the bandwidth varies all over the place. So anytime in many devices you see some static buffer size, it can't possibly be correct. And it can, and as you'll see, will bite you. How many of you have had experiences like this? I had this for the last 5 or 6 years as my own home network manager. At least some people in the audience have raised their hands. Every time I would try to seriously debug this, the network would stop misbehaving so much. And a little over a year ago, I got this in spades one day and knew that I had to chase it because I'm supposed to be working on immersive teleconferencing and a network with over 1 second's latency with huge jitter, which is somewhere between here and the moon and moving back and forth at a high fraction of the speed of light, is not something you're ever going to successfully do that on. And so I was trying to figure this out and thought it might be Power Boost, and ended up having lunch with one of its creators. The morning of this, we talked for a long time that day. I finally figured out how to tickle the problem for real. And basically it was a really simple test from my house to a machine 10 milliseconds away at MIT. So that morning I figured out how to do it, but I hadn't played with it very much. So we talked about a pile of things. I talked with Rich Woondy, and he mentioned well, it could be Power Boost, but probably not. He thought it would more likely be the big buffers problem that Dave Clark had been warning about. He also told me that, well, red was often not being turned on by some of the network operators. Why? Because I sort of thought that AQM was old hat in the 1990s. Things like also ECN weren't working, but I don't have time here to really talk about ECN at all today. And he also gave me a pointer to the ICSI Nettalyzer project, which played a pivotal role in understanding just how much trouble we're in. So I got my real smoking gun the next day with SmokePing. This was my home network as I moved 20 gigabytes of data from my house to MIT. And those are seconds, and yes, there's lots of packet loss. And the only time the behavior is reasonable is even surfing the web was so painful, I had to suspend my transfers from time to time just to be able to get some email and do things. So complete brokenness. This is what a normal TCP trace might look like, and so I was motivated enough to take a packet capture and eventually plotted it up a few weeks later. I hadn't done any of this sort of stuff since I was working on HTTP in the 1990s. And instead, what I got out was this. These amazing spikes. You see those the red lines are most interesting. This is the outstanding data the TCP has in flight. This doesn't look like a normal TCP sawtooth at all. Those spikes are like 10 seconds apart. There's of order half a megabyte in transit at once over a 10 millisecond path. That's way more than you'd ever want to see for a 10 millisecond path. So what in the world was going on here? It looked like nothing I did, and later we verified it really wasn't my cable at all. A week or two later, I was down in New Jersey and did the same sort of tests on FiOS service and got very similar results. They tend to be rattier because I had no way of locking the rest of the family out, and there was some interfering traffic, but essentially the same pattern. In this case, 200 milliseconds latency, quarter megabyte of data in flight on symmetric 2525 service. 200 milliseconds of latency, this is way more than it ought to be over a 20 millisecond path from New Jersey to MIT. And wireless is even worse, and I didn't understand why it might be one or the other. So I ended up calling for help at this point. And we had a lengthy email thread discussing what was going on in these traces. And it's not a pretty sight. There are very large buffers in this path, in this particular case in the cable modem or the FiOS CPE. And it's so bad that we've actually defeated TCP congestion avoidance. So the hosts are not backing off when they should. We're inducing congestion. We're inducing these spikes of really nasty packet loss along the way. So I'm seeing significantly more packet loss than a normal TCP would normally have at this point. So the attempt by buffering to avoid packet loss is actually coming back to bite you and making it worse. Classification doesn't help you. These devices have like one queue, and there's no fair queuing. There's nothing that you can get. Once you've dumped packets into these queues, you're stuck. They'll come out the other side no matter how hard you try. Well, what can trigger this kind of problem? Anything that saturates the network will do this. So I'll give a few simple examples, things like uploading a video to YouTube, or I found Google Chrome, which with my permission was uploading its dead corpse to Google one night when it had crashed. Email with large attachments, BitTorrent, more about that later. Just file copies, which is what all I was doing. Of course, if you run TCP on top of TCP, you're going to lose completely. Downloading movies could potentially do this to disk. In other words, anything that saturates. Video streaming itself doesn't necessarily saturate the link, but it means that you have much less headroom to saturating. And when you do saturate from other traffic, then it'll go on for much longer. More insidiously, but I don't have time here, is even web browsing does this when you hit a website with lots of images on a page, you can end up with 100 or more packets flying all at once to the poor broadband connection where it goes kasplat and fills those queues about it. So there's transient behavior that also is happening, and the web guys need to clean up their act too. But that's not all the bad things that happen. DNS starts to have failures. So I, in my traces, found a few DNS lookup failures. Of course, adding a second or two of latency really kills your browsing experience. Lots of other things break. ARP, DHCP, you know the whole thing. God forbid you try to do voice over IP over a saturated link with anything like this kind of buffering, you will completely lose. Web browsing will cause transient dropouts. Everything suffers. Just think, what protocols do you run that will die with bad timeouts and when they see the wrong packets getting stepped on? Okay, a year ago, The Nettalyzer folks were here. I don't know, since I wasn't here, I don't know, at Nanog, I don't know who did the presentation. Early versions of this data set were presented then. And this is for both upstream and downstream. This shows the inferred amount of buffering in the broadband edge. And the actual amount of latency, you can see, depends upon the lines. The dashed line I put in here is 150 milliseconds, which has been the normal telephony standards for what is, quote, good enough historically for long before even the internet came along. But the next green line is half a second. You're up at 4 seconds down here, and this is where the test just stops trying to do stuff. So as you can see, most of our broadband edge has excessive buffering. Sort of end of story. ICSI has just, closed the case on this particular problem, that it exists and it's massively pervasive. What they didn't have last year was a split by the different technologies. The different color dots makes it obvious that it's in cable, DSL, and fiber alike. The only question is really of one of a degree. So our broadband edge is broken. Unfortunately, it doesn't stop there. And I want you to end up as paranoid as I now am about excessive buffering. So I had seen some strange behavior last summer as I was poking at things I did not understand. So I did more work at home. For example, during my tests, I caught my home router as observed from outside with literally like 8-second latency at one event. Much worse than broadband. What in the world was causing this? This is a stock recent commercial home router. And at this particular instant, I'd upgraded my service to 5010 service at that instant when I happened to do this particular thing. So before going public with this, I really want to understand what's causing this too. And it didn't stop there. So having seen this insanity, I played with 3 or 4 different home routers and found similar sorts of behaviors. And then I eventually wanted to actually play around myself. So I installed OpenWRT on one of them and started playing with one of the knobs I suspected ought to be able to control the latency. On many of these routers are running Linux. The problem is not unique to Linux, but on Linux there's this transmit queue length you can control. And I set that to 0 on the router, and nothing happened. I started tearing my hair out, and 2 days later I remember, I was copying upstream, so the buffers have to be in my host operating system, in my case Linux. So this case occurs anytime your broadband bandwidth exceeds how many bits you're actually able to get over your wireless link. The bottleneck's not going to be in the broadband gear at all. It's going to be in that final hop. So we have to fix both the operating systems, which is more detail about what's broken there, and our home routers as well. So unfortunately, buffers started digging into this, hide in modern operating systems all over the place. But I want to try to help you understand how sensitive things are to this. So if you have 256 packets of buffering and you're able to get 10 megabits a second over your wireless link, which is not unusual, that's 1/3 of a second of latency right there by simple arithmetic. And things will fill those buffers. What happens in a busy conference? Thankfully not this one. I am in awe of the quality of the network here. So there is hope. Where your fair share might be 100 kilobits, well, the same amount of buffering becomes 30-second latency. Well, you've just lost completely, and along with the additional packet losses you get in various ways. So you can ask yourself, as I was for a while, why won't I see this on Ethernet? And of course, as I started to understand what I was doing, I did plug the 1 gigabit per second NIC into a switch, and it turns out that the device drivers or the hardware has now sprouted these ring buffers internally, and they're typically on all of the operating systems, as far as I can figure out, about 256 packets of buffering sitting down in your device driver underneath whatever the operating system queuing and classification might be. You don't see it on Windows, interestingly, and I groveled around on Microsoft's website, and they actually bandwidth limit their traffic, so they never quite saturate 100 megabit per second link. I think they saw Bufferbloat and adopted a very nice pragmatic solution to this, at least for a campus network. And I recently was looking at Ethernet switch chips, which have 1 or more megabits of RAM internally. We were playing with Dave Tott's been playing with a modern home router, and we were seeing 70 millisecond latency in the switch itself. So some of these devices, even individual chips, are having large amounts of buffering there, well beyond what is probably necessary. So where does this hurt us? Well, lots of places. Trying to keep us oriented by sort of this, using this sort of the same map everywhere, because our operating systems, which are also in these guys, have problems, and our laptops, it's sort of all over the edge of the network there. Okay, so in the 1990s, I know I suffered with the rest of people here, or many of the people here, with the very large congestion problems we had then. But it doesn't stop there. The same kind of thing now can occur in lots of places, in particular in wireless technologies. People have put in lots of buffers for lots of reasons that seem sensible. The problem is they're statically sized and unmanaged buffers. For example, in 3G, there's various stuff to try to deal with error correction, which can add pretty large amounts of buffering. The wireless protocols themselves have interesting things. You end up with a situation where the aggregate buffering all over the network, when it saturates, has a real problem. So if you've wondered why various of the 3G carriers have had very high latency, you should stop wondering. It's basically the same kind of phenomena we had in the core of the internet in the 1990s in large part. Dave Reed tried to make people aware of this about a couple of years ago. I've personally seen 6-second latencies. I've talked to other people who've seen up to 60-second latencies. I can confirm now that this is a problem in at least some RNCs, probably all of them, as far as I would guess, but also certain carriers not doing the right thing in their backhaul networks that are running congested. Okay, so why, given that we sort of thought we had the congestion problem solved in the 1990s, is it clearly not just turned on everywhere? And so that was one of the questions that I needed to understand. And so I called up Van Jacobson several times last year. Told me the interesting story here. Thankfully, it has some amusing things. Since I'm bearing bad news, I like to have some funny stories as well. So, something over 10 years ago, in 1999, Kathy Nichols walked into Van's office and showed to him over a couple-hour period that Red had several pretty fundamental misfeatures, and they tried to publish this result. The first time they tried to publish the result with maybe a possible solution for it, the paper was rejected because Van had chosen to explain the TCP servo system a flush toilet, and this offended one of the program committee members. And then they tried again in like 2004, blinded conference submission, and the reviewer's comments came back that that the authors can't possibly know, need to understand how AQM actually works, and they should go read Floyd and Jacobson, 1993. There is a draft of a paper called Read in a Different Light from 1999 that did escape. It'll give you some insight as to the problems. There's also a potential, I don't know how big, for time-based congestion, which is the thing that causes me to lose sleep a lot. People are not pacing packets out, and they're injecting them in bursts in the network. This is also making it much harder to deal with queue management at the edge. So the question is, will we start seeing global or regional synchronization phenomena causing time-based congestion in the network? Don't know. We'll see. So we see this in a number of locations. Unfortunately, some carriers are not enabling red even in places where they could and should. For example, in the head-end gear of broadband. Certainly the wrong things are happening in a lot of the current 3G networks. Some pieces of the internet, it's clear the operators are running naked in places where they shouldn't. I've certainly verified that just by looking at the latencies going back on certain networks. I've seen satellite latencies of insanity to Peru. You often see this in hotels for lots of reasons that have to do with it. We have lots of problems in 802.11. Again, ultimately you have to worry about even a single packet of buffering in many environments is a real issue. And we aren't controlling our buffering dynamically. So it's a real headache. The result of this is a real mess, and it's why it's been hard for people to figure out. Every other conference I've been to, I've seen problems in 802.11, not here. Schools, hotels are particularly notorious, like I see in my across the street. And it's hard to figure this out. We had our network completely fail at one laptop per child when I was there. Bufferbloat was certainly one of the two causes that caused this real grief, and we never figured it out then. There's tons of different places where buffering can hide in our systems, all the way up into applications themselves. I don't have time to go through this, but it's a long list, and VM systems are adding yet more layers of potential buffering. Corporate networks are another issue. For example, I discovered that our own internal corporate network, while we are running very sophisticated classification for VOIP and so on, has no queue management enabled. And I'm in the process of getting this fixed. When Windows 7 takes over from Windows XP in corporate environments, this will become much more of an issue. Windows XP does not turn on window scaling by default, and so won't typically saturate most corporate long-haul links. Everything else does. I've seen problems in our IPsec infrastructure at the point where it comes down. There are lots of other places you need to worry about, encryption buffers and so on. So where do we have problems? Unfortunately, we're now most of the internet. Not always. There are some places, some people run really clean networks. My hat's off to them. The hypothesis is people operators who grew up in the 1990s who were burned badly by congestion then. You can do some things about this. You can even make your home environment work much better. This is my before, and my after is almost 100 times better. I have to throw away a lot of my bandwidth to do it. There's more information on my blog and so on about what to do where. There are a couple of interesting implications about having to do with network neutrality in all of this. I don't believe BitTorrent problems, I believe that part of the problems that BitTorrent causes were incorrectly diagnosed. At the time that BitTorrent deployed, the buffering was already excessive, and at the time the uplink was very low. You'd end up with multiple second latencies when BitTorrent was saturated with it, and XP makes it much harder to see this because it's going to take multiple connections to do it. Carriers telephony have a fundamental advantage of quality over conventional SIP voice or Skype. That's reality. I don't believe this was intentional by anybody. The carriers get this in the ear or in the inbox when in terms of complaints about their networks not working properly. If we don't roll up our sleeves and fix this, if we want to do anything in low latency, we have a real problem. So the situation is getting worse, in part because XP is going away, but also that the application mix is changing, and I fear for things like femtocells and the like. So it's going to get worse rather than it gets better. If you don't know what the buffering is in your devices, it's a bomb waiting to maybe or may not ever go off for you, because it only matters at the bottleneck link. Obviously, you can push back on the suppliers. The tests are actually pretty easy. You just test latency under load. You saturate any link and measure its latency. Buffering should never be static. So there are changes, thankfully, underway in DOCSIS to allow them to control the amount of buffering in cable modems. But we have to get everybody to go beyond the thought that packet loss is evil. It's actually essential for the network to work properly under load. And that message has to get into the customers' and everybody's minds. Take RFC 2309 to heart. If you're in a situation where you can run red, you should be, with some possible exceptions, but I don't have time to go into that. The big place where it's obvious that's not happening is in a lot of the broadband head ends. To really fix this properly, as opposed to just reducing the problem, is going to require at least AQM everywhere and better algorithms, along with probably ECN and a bunch of other good things getting deployed. One message for people who run networks in this place: you guys take it in the ear and the inbox, even when it's somebody else's bloat. Okay? So it can be the person's operating system, it can be their home router, but you're the guys who get blamed when the internet doesn't work the way it's supposed to. And I know, because I've placed those service calls personally. And thank you, whoever set up this network. It's the first time I've seen a decent network anywhere on the planet. I'm actually running on my Linux machine an algorithm that controls my buffering on it, and so now we have to fix the rest of the planet. So we're all in this together. Please come help. Think about all the places where you may have problems. There's a longer version of this talk up on YouTube that I gave at Google a month or 6 weeks ago. And questions? Come now. No, at the IETF, it was exactly the opposite. Everybody ran to the microphone.
We have a couple minutes. Hello. Oh, there we go. We got a couple minutes for questions or comments here. Thanks.
Kevin Oberman from ESNet. Bufferbloat is so pervasive. I mean, it's basically everywhere and in everything. Has anybody looked into any way that we can modify TCP congestion algorithms to recognize and account for bufferbloat? It creates such a very distinctive signature in the traffic flow. I would think there ought to be some way we could detect this and compensate for it, if not truly correct for it.
Well, yeah, then you have the deployment problem of the modified TCPs. Game theory tells you that if that puts you at a disadvantage to everybody else, that you're not likely to get it deployed. What's worse is it's often what you do to other people or they are doing to you on the shared link. And so just because you made your personal machine work better and be more friendly, that doesn't mean you aren't the poor person who's dying from it. It may be, and what I was doing to my family was when I was typically copying big stuff to my house for my job, right? And so I was usually the inflictor of pain. So I think that it's often going to be easier to fix it in the places where we have the biggest problems faster. I mean, upgrading a lot of this stuff in the field is really hard. So, but fixing, it's not that I just think that better TCP algorithms aren't a good thing, just that I'm pessimistic about actually getting them out there.
I appreciate your pessimism, but I will remind you that it wasn't that long ago that Windows did not do slow start. And that gave them a definite advantage in many respects, and they do slow start now.
Yeah.
So it's not hopeless. Just
it's not hopeless, but it's hard. I mean, I think we have to attack this in all directions we can.
Just one more, folks. After these two speakers, we're going to close the mics and move on to the next talks.
Randy Bush, IJ. Jim, as I said, discussion with you a year ago, most of us here are transit providers.
I'm having a little trouble hearing you, Randy.
Is that a bug or a feature? Most of us here are transit providers. The in-the-can available approach to all of us is WRED.
Mm-hmm.
How many people here have WRED turned on? Exactly. How many people do not have WRED turned on because parameterization is very confusing and you don't know what to do? That's a shame, because what I was going to suggest is, as I was just discussing with Sharon, a tool to give you a good guess at the WRED parameters, which are difficult. It is an undergraduate level project. So I think, you've been saying this.
I think that's great. And the big challenge we have is not so much in the transit part of the network, but in the edge, in homes and wireless.
You see the edge, but we've got routers that are sitting between, Sacramento and LA or San Francisco that have buffers sized for Transpac.
Yeah, and when they saturate, you'll have problems.
Thanks.
Steve Feldman from Nanog. So thanks for telling us that our network here is wonderful, but I'm kind of curious as to why it's so wonderful compared to what you normally see.
Well, I think there are a couple of things going on here. One of which is that the people who do enterprise access points have a lot more of a clue than the people who build the home router kit, which are repackaging general purpose operating systems. So at least you don't have the home router disaster here. I noticed, I guess there was Cisco access points back here that looked to be the industrial versions. The rest of it is, I think you're probably running red every place you should, locally at least. And the last reason I saw good behavior is that I'm running a modified Linux kernel that's very carefully, much more carefully controlling its buffers over that wireless link. So my latencies don't go crazy even when I copy a 100 megabyte file, because my laptop's got a kernel that isn't as insanely over buffered as most other kernels are. That's the last piece of this equation that isn't out there in the operating system area.
Tony Capella, 5 Data. If I could add one comment to the why, or part of the answer, if I may be so bold. There's a presentation from Nanog 38 that we did in St. Louis where we first tried so-called QoS, or different scheduling, application-based, or rather packet intent, if you will, scheduling on the Wi-Fi. And it discusses what we did there and have been doing since at Nanog on the wireless specifically. And I think that contributes at least a small bit to a reasonable experience.
Yeah, but part of the reason why this is getting worse for most people is that a lot of the chips that first got designed for data centers, which have these very huge ring buffers, have migrated into our laptops. And so our laptops 5 or 6 years ago were often running with much tinier buffers than we have today on a modern laptop, running effectively the same chip as you might find in a data center. And so the buffering by default, same device driver, same default settings in the operating systems is typically, at least when we looked at all the Linux drivers, in between 200 and 300 packets sitting there. Maybe sort of okay on receive, but for transmit it's the kiss of death.
Thank you very much, Jim. We appreciate that.